Welcome to 5-Minute BTech channel. So, let's talk about a simple idea. For every single computing problem out there, there's a special type of operating system designed to solve it. This is definitely not a one-size-fits-all world. Let's dive right in.
First up, we've got the batch operating system. Just imagine you have to run thousands of really repetitive tasks, like a company's entire payroll. Having a person sit there and click start for each one, that would be an absolute nightmare, right? Well, this OS was built to be the ultimate workhorse for exactly that kind of problem.
You see, the whole concept here is the batch. Think of the OS like a factory manager. It doesn't really care about one single job. Instead, it waits until it has a whole big stack of similar ones, like printing 1,000 bank statements, and then it just runs them all at once, one after the other. It's basically a data processing assembly line.
And the process itself? It's brilliantly simple. You, the user, you just submit your job, and that's it. You walk away. The OS takes over, bundles it with other similar jobs, and just powers through the entire batch without any more input from you. There's literally zero direct interaction. You drop it off, and you come back later to pick up the results.
Now, as you can imagine, this whole approach has a pretty clear trade-off. On one hand, it's incredibly efficient for these huge repetitive tasks, but the big downside is how inflexible it is. You can't interact with your job once it's started, and if something goes wrong, well, good luck. Debugging is a really slow, painful process because you usually only find out about an error after the entire batch has already failed.
But that brings up a really big question. What happens when a job in that batch needs to do something slow, like read data from an old tape drive? The super-fast CPU just sits there, waiting and wasting precious time. This inefficiency was a huge problem, and it's what led directly to the next evolution in operating systems.
And that's where the Multiprogramming OS comes in. This is pretty much the core idea behind the computer you're probably using right now. If the batch OS was a workhorse, this one is a master juggler. It's designed with one main goal: keep that CPU busy every single millisecond.
See, the whole idea is to load several programs into memory all at the same time. It's kind of like a chess master who's playing 10 games at once. The second one opponent stops to think, the master instantly moves to the next board. A multi-programming OS does the exact same thing, but with computer programs.
And here's where the magic happens. When Program A needs to do something slow, like read a file from the disk, the OS doesn't just sit there and wait. Nope. It instantly pauses Program A and gives the CPU to Program B. This constant, super fast switching is what lets your computer run a browser, music, and a bunch of other apps all at once. It dramatically boosts the whole system's performance.
The payoff here is huge. You get sky-high CPU utilization. But all of that juggling isn't easy. The OS itself has to become way more complex. Now it has to manage memory for all these different programs and constantly decide which one gets the CPU next. So, all that efficiency comes at the cost of complexity.
Okay, so we've made our computers super efficient. But what about those times when timing isn't just about performance, but it's about safety? What about systems where a delay of even a few milliseconds could be an absolute catastrophe?
Well, that brings us to our third type, the real-time operating system, or RTOS for short. This one isn't about being the fastest. It's about being the most predictable. This is the precision expert of the OS world.
For an RTOS, the #1 absolute priority is meeting deadlines, period. It's used in things like industrial robots, airplane controls, and critical medical equipment, places where an action has to happen within a guaranteed window of time every single time. In this world, predictability is way more important than raw speed.
Now we've got to talk about two different flavors here: hard and soft real-time systems. In a hard RTOS, like the one that controls a car's airbag or a pacemaker, missing a deadline is a catastrophic failure. End of story. But in a soft RTOS, like for video streaming, if a frame drops here and there, it's annoying for sure, but the whole system doesn't fail.
This level of precision and reliability, it comes at a pretty steep price. An RTOS often needs specialized, expensive hardware, and the software design is incredibly strict and complicated. You just don't get this kind of guarantee for free.
So we've figured out efficiency and precision for a single machine. But what's the next frontier? What do you do when the problem is so enormous that no single computer on the entire planet is powerful enough to solve it?
Well, that's when you build a distributed operating system. This is the global collaborator.
The kind of OS that powers the modern cloud by linking tons of computers together so they can act as one giant brain.
The real magic here is the powerful illusion it creates. A distributed OS takes a whole network of separate, independent computers and makes them appear to you, the user, as one single, incredibly powerful machine. You don't see the hundreds of servers working behind the scenes, you just see one seamless system. So this system basically has two superpowers: scalability and fault tolerance. Scalability means you can just keep adding more computers to the network to get more power. And fault tolerance means that if one of those computers fails, the system doesn't crash. The OS just cleverly routes the work around it, and everything keeps on running.
The benefits are obviously immense. You get incredible power and reliability. But the Achilles heel here, it's all completely dependent on the network that connects those machines. And as you can imagine, designing and maintaining an OS that can manage thousands of computers is just mind-bogglingly complex.
So as we wrap things up, what's the big takeaway from all this? It's pretty clear. There's no such thing as the single best operating system. The real question is always, what's the right tool for the job?
We looked at 4 totally different problems, and each one had its own clever solution. The batch OS for raw, repetitive power, the multiprogramming OS to stop wasting precious CPU time, the real-time OS for tasks where deadlines are absolute, and the distributed OS to get a level of scale and reliability that no single machine could ever hope to achieve.
So I'll leave you with this to think about. From the Internet of Things to AI-driven everything, our computing needs are changing faster than ever before. What kind of problem do you think the next great operating system will be designed to solve? What's it even going to look like? If you like the video, hit like and subscribe to the channel, and I'll meet you in the next video.